Tonight, we're going to talk about a ship designed to reach another star. And we're going to explain why, according to everything we currently understand about physics, biology, and human nature, that ship would almost certainly fail. Not somewhere out in the dark between the stars, but far closer to home than you'd think. It sounds like the beginning of a rescue story. A crew stranded in interstellar space, alone, adrift, millions of miles from anywhere. But here's what most people don't realize. The most likely place for a generation ship to fail isn't interstellar space at all. It's the part of the journey most people don't even think to count. The hundreds of years it would take just to cross our own solar system's outer edge, the vast, dark, mostly empty shell surrounding the sun that most people have never even heard of. A ship built to sail to another star might collapse before it ever technically leaves home. For over a century, this idea, the generation ship, has stood as science fiction's most elegant answer to an impossible physics problem. No faster than light travel, no convenient wormholes. Just time, patience, and a self-contained world large enough to keep a human population alive, breeding, and functioning for centuries. It's a beautiful idea. It's also, according to nearly every field of science we can bring to bear on it, radically harder than the fiction ever let on. The first surprise is the sheer, punishing scale of the problem. A scale so large that leaving the solar system turns out to be a centuries-long ordeal in its own right before interstellar space even begins. The second surprise is that the single hardest technical problem isn't the engine, it's breathing. Every closed ecosystem humanity has ever actually built and sealed shut has failed, and the way it failed reveals something deeply humbling about how little we understand our own planet's life support system. The third surprise is a mathematical wall so absolute that the numbers involved stop being numbers at all and become something closer to nonsense. Figures with thousands of digits, physically meaningless, and yet mathematically unavoidable given the fuel technology we actually possess. And the fourth surprise, the one that turns this from an engineering problem into something far stranger, is that even if every mechanical and ecological problem was somehow solved, the ship might still fail for a reason no equation can fix. No group of human beings in the entire recorded history of our species has ever managed to sustain a single, stable, cooperative society for as long as a generation ship's voyage would require. By the end of tonight, you're going to understand exactly why a generation ship, humanity's most ambitious proposed answer to the vastness of space, would very likely fail, and fail early, and why the specific ways it would fail tell us something remarkable about what it would actually take to become a species capable of building one. Before we dive in, if you're someone who finds this kind of honest, unhurried exploration of the universe genuinely calming, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start with the idea itself, because it's worth understanding exactly what problem the generation ship is trying to solve, and why serious scientists still take it seriously despite everything we're about to walk through. Imagine a cruise ship that never docks. Now imagine that the passengers' great-grandchildren, and their great-grandchildren, and theirs after that, will all be born, live entire lives, and die aboard that same vessel, sailing an ocean so vast that no horizon is ever reached within any single human lifetime. That is the generation ship in its simplest possible description. Not a vehicle that carries people to a destination. A world that moves. The logic behind the idea is straightforward, and it starts from a wall that physics simply will not let us walk around. The speed of light. 299,792 kilometers per second is not a suggestion. It is, as far as anyone has ever measured, an absolute cosmic speed limit built directly into the structure of Einstein's special relativity. Nothing with mass can reach it, let alone exceed it. And the nearest star system to our own, Proxima Centauri, sits 4.2465 light-years away. Even a spacecraft that could somehow travel at a meaningful fraction of light speed, something no technology that currently exists could achieve for a human-carrying vessel, would still need years to decades to make the crossing. At the actual speeds our best real spacecraft have ever achieved, the number balloons into the tens of thousands of years. So the generation ship proposes a different kind of solution. Not a faster ship, a more patient one. If you cannot make the journey short enough to fit inside one human lifetime, you make the ship a world instead. A closed, self-sustaining habitat, carrying a population large enough to reproduce, to raise children, to grow food, to recycle air and water and waste, and to maintain the vessel itself across dozens of generations. The people who depart know they will never arrive. The generations born in the middle of the voyage will live and die, having known nothing but the ship. Origin and destination alike reduced to stories, half-remembered myths about a green planet nobody alive has ever stood on, and a new star nobody alive will ever reach. Only the final generation, born centuries after the ship's launch, would ever actually see the destination with their own eyes. This isn't a new idea. One of its earliest and most haunting fictional depictions comes from Robert A. Heinlein's Orphans of the Sky, first serialized in 1941. A story in which the crew has been aboard so long, across so many uncounted generations, that they've forgotten they're on a ship at all. To them, the vessel simply is the universe. There is nothing outside it, because nothing outside it has ever been seen. But the idea has moved well beyond fiction. The most serious contemporary academic effort to actually design one is called Project Hyperion, launched by the Initiative for Interstellar Studies in December 2011. A genuine, ongoing engineering and design program, complete with a global competition that ran through the final weeks of 2024, drawing real proposals from real researchers trying to work out, in detail, what such a ship would actually need to contain. Scientists have even developed a rough taxonomy for the concept. World ships, carrying more than 100,000 people. Colony ships, somewhere between 1,000 and 100,000. Sprinters, small crews of under 1,000 traveling at more than 10% of light speed. And slow boats, small crews traveling at more modest velocities. Every category, notice, assumes hundreds to thousands of years in transit. There is no fast version of this idea. There is only slow and slower. Why not simply freeze the crew and wake them at the destination? Suspended animation, cryosleep, is one of science fiction's favorite shortcuts, and it remains exactly that, fiction. No verified method currently exists to freeze a living human being and revive them without catastrophic, irreversible cellular damage. Some researchers have looked at the natural hibernation abilities of certain mammals for inspiration, wondering whether something similar might someday be adapted for humans. But this remains, honestly and completely, in the realm of speculative future research, not a solution anyone can currently build, which leaves the generation ship as the only remaining option once faster-than-light travel and suspended animation are both taken off the table. Send a living, breeding, self-sustaining community and let time, vast, patient, indifferent time, do the rest. Let's put some real numbers on exactly how much time. Traveling at 10% of light speed, roughly 30,000 kilometers per second, a velocity no crewed spacecraft has ever come remotely close to achieving. The trip to Proxima Centauri would take about 43 years. That's feasible, in principle, for a small sprinter crew, though it would still likely stretch across at least part of a human lifetime. Drop to 1% of light speed, about 3,000 kilometers per second, and the journey balloons to roughly 430 years. A genuine multi-generational voyage, spanning something like 10 to 15 generations. Drop again to 0.1% of light speed, 300 kilometers per second, still a velocity far beyond anything we could currently sustain for a vessel of any real size. And you're looking at roughly 4,300 years, more than 100 generations, one following another, in unbroken succession. And if you travelled at the actual speed of the fastest spacecraft humanity has ever built, Voyager 1, moving through space today at approximately 17 kilometers per second, the journey to Proxima Centauri would take roughly 75,000 years, something in the neighbourhood of 2,500 generations. Let that number sit for a moment, because it deserves to. 75,000 years ago, Homo sapiens were not alone on this planet. We shared it with Neanderthals, a separate human species, still walking the Earth alongside our own ancestors. The entirety of recorded human civilization, every written word, every law code, every empire, from the very first cuneiform tablet to the device you might be listening to this on right now, spans roughly 5,000 years. A generation ship travelling at our current best real-world speed would need a stable, functioning society to persist for 15 times the entire length of recorded human history. That is the scale of patience this idea actually demands. And we haven't even gotten to the hard parts yet. Let's actually try to feel the distance involved, because 4.2 light-years is a phrase that slides past most people without leaving a mark, and it deserves better than that. Proxima Centauri sits 4.2465 light-years from Earth, approximately 40.21 trillion kilometers away. Light itself, the fastest thing that exists anywhere in the universe, needs more than 4 years to cross that gap. If you switched on a flashlight and pointed it at Proxima Centauri tonight, those photons would still be travelling through the dark, alone, uninterrupted, when the calendar reaches the summer of 2030. Translate that distance into something a human body can relate to. If you drove a car at a steady highway speed of 100 kilometers per hour, never stopping, never sleeping, never once pulling over to refuel, the journey to Proxima Centauri would take approximately 46 million years, longer than the span of time separating us, right now, from the extinction of the dinosaurs. Or try it this way. Imagine the sun shrunk down to the size of a basketball, sitting on home plate of a baseball stadium. On that scale, Earth becomes a single grain of sand, orbiting about 25 meters away out in the dirt of the infield. The entire inner solar system, every rocky planet, every gas giant out to Neptune's orbit, fits comfortably within the first few dozen meters of that same infield. And Proxima Centauri, on this same shrunken scale? Another basketball, sitting roughly 6,700 kilometers away. That's the real-world distance from New York to Berlin. The nearest star in the entire universe, shrunk down to a scale where our own sun fits on a baseball field, still ends up on a different continent. This is what nearest actually means once you take the word seriously. Now, here is the detail that most casual treatments of interstellar travel simply skip past entirely. And it's the detail this whole story turns on. Before a generation ship can even begin its true interstellar crossing, it first has to leave the sun's own sphere of influence. A vast, invisible bubble called the heliosphere, inflated by the outward pressure of the solar wind, the sun's own breath pushing outward against the pressure of the wider galaxy. Voyager 1, humanity's most distant spacecraft, crossed the outer edge of that bubble, the heliopause. On August 25th, 2012, at a distance of roughly 121 astronomical units from the Sun. That crossing came 35 years after Voyager 1's launch in 1977, and it happened only because the spacecraft received powerful gravitational slingshot boosts from Jupiter and Saturn along the way, adding speed it could never have generated on its own. And crossing the heliopause is not the same thing as leaving the solar system. Not even close. Beyond the heliosphere lies the Oort cloud, a vast, roughly spherical shell of icy debris that astronomers believe genuinely marks the true outer edge of the Sun's gravitational domain. Current estimates place the inner boundary of the Oort cloud somewhere between 2,000 and 5,000 astronomical units from the Sun. The exact figure remains genuinely uncertain, since we've never directly observed it, and the full structure may extend outward as far as 100,000 to 200,000 astronomical units. That outer figure works out to nearly 3.2 light-years. which means the Oort cloud alone, our own solar system's outermost, most distant edge, may account for something like 75% of the entire physical distance to Proxima Centauri. Voyager 1, after nearly 50 years of travel, the longest sustained journey any human-made object has ever completed, at the highest speed any human object has ever sustained, has reached a distance of roughly 164.7 astronomical units from the Sun as of recent tracking. It has not yet reached even the inner edge of the Oort cloud. At its current rate, it won't get there for approximately another 300 years. Sit with that. 300 more years for the fastest, farthest travelling object our species has ever built, just to reach the beginning of our own solar system's outer boundary. A boundary that isn't even the edge of interstellar space. It's simply the edge of home. Here is where the title of tonight's exploration earns itself, and where the first real shock of this story lands. A generation ship bound for Proxima Centauri isn't just designed to survive 4+ years of interstellar cruising at some fraction of light speed. It has to survive the centuries it would take simply to climb out of the Sun's own gravity well and cross the Oort cloud, a region so vast, so dark, and so poorly mapped that we still don't know its precise inner boundary, only a working range. Any generation ship would spend its first century or more still within the Sun's gravitational and radiation influence, close enough, in strictly cosmic terms, that rescue or resupply from Earth might remain theoretically imaginable, yet so far away already that a single message, sent at the speed of light, would take hours to days to arrive one way. This is the implication that most conversations about interstellar travel simply never reach, because most conversations about interstellar travel jump straight from launch to arrival, skipping over the centuries of transit that happen before the ship has even technically left its own star system behind. A generation ship's ecology, its power systems, its social fabric, its entire closed world. All of it must function perfectly for a minimum of roughly 300 years before the heliosphere is even a fading memory in the ship's rearview mirror. If a closed ecosystem cannot sustain itself for the 300 years it takes just to cross the Oort cloud, the ship has already failed. It failed before it left home. Not metaphorically, literally, in the most precise sense of the word home that exists, the gravitational neighbourhood of the star that raised our species. This is shocking discovery number one. The hardest part of a generation ship's journey isn't necessarily the interstellar crossing at all. It's simply escaping our own solar system's outer shell. A task so large, so slow, and so unglamorous that most people planning this kind of voyage in their imagination never even think to budget time for it. Let that settle for a moment. And then, let's talk about what would actually have to work, without failure, for every single one of those 300+ years. Because the next problem is not a problem of distance. It's a problem of breath. A generation ship has to be a perfectly sealed terrarium. A world where nothing meaningful enters and nothing meaningful leaves. Where every exhaled breath, every drop of sweat, every human waste product, every fallen leaf is captured, broken down, and rebuilt into food, oxygen, and clean water indefinitely. Not for a weekend camping trip. Not for a single year, for centuries. The technical word for this is closure. The degree to which a system recycles its own materials without needing anything from outside. And here's where the numbers, which sound genuinely impressive at first glance, quietly turn against you. On the International Space Station, NASA has achieved a genuine milestone. 98% water recovery from crew, urine, sweat, and cabin humidity. 98% sounds, reasonably, like a triumph. But that remaining 2% is where the real story lives. For a crew of 4 using roughly 12 litres of water per person per day, a steady 2% daily loss works out to about 0.96 litres lost, every single day, forever. Run that math across a 250-year voyage, and you arrive at a staggering figure. Approximately 87,600 litres of water, permanently and irrecoverably lost. An entire swimming pool, draining slowly into the void, drop by drop, with no faucet anywhere in the universe to refill it. And water, according to researchers who study this problem closely, is the easy one. The harder problems involve gases, and nitrogen sits at the center of the difficulty. Analysis by researcher Alex Tolley, published through the Centauri Dreams Research Forum, makes the point plainly. Recycling systems don't provide a reliable primary source of usable nitrogen for new plant growth, because significant quantities are inevitably lost to the air as inert nitrogen gas through uncontrollable microbial processes. A fully closed environmental control and life support system, in Tolley's own careful assessment, is probably impossible. At an absolute minimum, hydrogen, oxygen, nitrogen, and carbon lost through airlocks and imperfect recycling have to be continually replaced, along with nutrients that get locked away in the very materials the ecosystem itself produces: soil, wood, fiber, and waste chemicals that never quite make it back into the loop. The ESA's Melasasa project, the microecological life support system alternative, launched in 1989 and still, to this day, considered the most advanced closed-loop life support research effort on Earth, approaches the problem by modeling an artificial ecosystem as a series of interconnected compartments, each one responsible for a different stage of waste processing and food production. And the project's own lead researcher, Christophe Lasseur, has articulated a principle worth carrying with you through the rest of tonight's story. For any closed life support loop, the efficiency of the complete system is entirely dependent on its single weakest process. A closed ecosystem is only ever as good as its worst recycling component. If one bacterial reactor operates at 99.9% efficiency, but a second one manages only 90%, the entire system quietly bleeds 10% of that material stream every single cycle forever. Now imagine a bucket with a slow, steady leak. Lose 2% of your water every single day, and you might not even notice at first. But compound that loss across 250 years, 91,250 individual days, and you haven't lost 2% of your water. You've lost, functionally, all of it, many times over. The same brutal arithmetic applies to every material cycle aboard a generation ship. Carbon, nitrogen, phosphorus, potassium, every trace mineral a human body and a functioning ecosystem require. Each imperfect cycle leaks a little. Over centuries, the leaks become floods. There's a deeper wrinkle hiding inside this, too. Recycling systems don't just need to recover raw elements. They need to recover them in the correct chemical form. Nitrogen lost as inert gas, the same gas that makes up 78% of Earth's own atmosphere, is completely useless to a growing plant until it has been fixed, chemically converted into ammonia or nitrates. On Earth, this essential conversion happens through billions of years of evolved partnership between soil bacteria and the plants that depend on them, supplemented by the natural electrical violence of lightning strikes. On a generation ship, that same nitrogen-fixing biological chain has to work flawlessly, without interruption, for centuries. Any break in that microbial relationship and the ship's entire agricultural system begins, slowly and invisibly, to starve. We don't have to speculate about how this actually plays out. We've already run the experiment, here on Earth, under conditions vastly gentler than deep space, and it failed in ways that are deeply, uncomfortably instructive. Biosphere 2 was the most ambitious closed ecological system ever built by human beings. A sealed 1.27 hectare complex in the Arizona desert containing 5 distinct engineered biomes: rainforest, ocean, savanna, desert, and marsh, alongside a dedicated agricultural zone and living quarters for its crew. 8 people, who came to be known as the Biosphereans, sealed themselves inside on September 26, 1991, intending to live there, completely cut off from any material exchange with the outside world for 2 full years. What happened next has become the foundational case study for anyone seriously thinking about closed life support. and every single failure mode inside it carries a direct, unsettling lesson for a generation ship. The first failure was the oxygen sink, and it's a genuinely fascinating piece of scientific detective work. Over the course of just 16 months, the atmosphere's oxygen content fell from a healthy 20.9% down to 14.5%. Equivalent, in practical terms, to permanently living at 4,080 meters of altitude, more than 13,000 feet up. The crew developed sleep apnea, chronic fatigue, genuine symptoms of altitude sickness despite never leaving sea level. And when the scientific team finally traced the cause, it wasn't biological at all. It was the concrete. The facility's massive structural concrete was quietly absorbing carbon dioxide through a chemical process called carbonation, reacting with CO2 in the air to form calcium carbonate, and in doing so, sequestering both carbon and oxygen directly into the walls of the building itself. The experiment's designers, some of the most visionary systems ecologists of their generation, had carefully modelled biological respiration and plant photosynthesis, accounting for every living organism inside the dome. They had not accounted for the building material. The missing oxygen wasn't leaking away into space. It was being chemically locked into the very structure meant to keep everyone alive. External oxygen had to be pumped in twice, in January and again in August of 1993, breaking the entire principle of closure the experiment existed to test. The lesson for a generation ship is direct and unforgiving. Unanticipated chemical reactions between ordinary construction materials and a sealed atmosphere can quietly destroy an entire closed system's gas balance. On a generation ship, with no outside oxygen supply to call in, a sink like that wouldn't be an inconvenience. It would be fatal. Every single structural material used aboard such a ship would need to remain chemically inert against its own internal atmosphere for centuries. A constraint that immediately eliminates most familiar building materials, including concrete, most steel, which oxidizes, and many plastics, which slowly outgas their own compounds over time. The second failure was ecological, and it unfolded almost like a slow-motion collapse of an entire imagined world. The engineered ecosystem was supposed to be self-balancing. Predator and prey, plant and pollinator, decomposer and waste, all held in a designed equilibrium. Instead, it spun out of the biosphere's control almost immediately. Most of the introduced vertebrate species died. Virtually all of the pollinating insects died. Cockroaches and an invasive tramp ant species exploded into the ecological vacuum left behind. Morning glories, a fast, aggressive vine, smothered the carefully designed rainforest biome. The desert biome, meant to stay arid, became unexpectedly waterlogged from condensation patterns nobody had anticipated. Even the trees grew wrong, spindly and structurally weak, because the glass structure blocked enough sunlight that they received only 40 to 50% of normal outdoor illumination, and because the total absence of wind meant they never developed the stress wood that gives a healthy trunk its natural rigidity. The lesson here cuts even deeper. Ecosystems do not simply work once you assemble the correct list of species inside a sealed box. They are dynamic, genuinely chaotic systems, capable of flipping from one stable state into a very different one with startling speed. A functioning ecosystem is an emergent property of millions of species interacting across evolutionary time, not a machine you can design on paper and expect to run as specified. On a generation ship, an ecological flip of this kind, pollinators dying off, crops failing, and invasive species outcompeting the food supply, isn't a recoverable setback that engineers can quietly patch. It is a death sentence, delivered slowly to everyone aboard. The third failure wasn't ecological or chemical at all. It was human. A second Biosphere 2 mission, launched in 1994 with 7 crew members, was intended to run for 10 full months. It collapsed after just 6, not because the ecosystem failed, but because the crew itself factionalized. Disputes with the outside management team escalated. 2 crew members were forcibly removed and replaced mid-mission, breaking closure just as thoroughly as the oxygen injections had. And the 4th failure, quieter but equally damning, was simple physical leakage. Despite being engineered as an airtight structure, Biosphere 2 lost roughly 10% of its total atmosphere every single year. On a generation ship, with no atmosphere to draw from beyond its own sealed hull, that leak rate would mean losing the equivalent of the ship's entire breathable air supply once every 10 years. Obviously, unambiguously fatal. Here is the lesson worth carrying forward through everything else we're about to cover tonight. Biosphere 2 had sunlight, filtered but genuinely present. It had a stable external temperature, moderated by the Arizona desert around it. It had 0 cosmic radiation to contend with. It had a real telephone line to the outside world, and external backup oxygen only a single phone call away. And it still could not sustain 8 trained, motivated, carefully selected people for 2 years. A generation ship has to do exponentially better than that, for exponentially longer. In an environment that is, in nearly every measurable way, exponentially harsher. Now let's leave the ecosystem for a moment and talk about something that isn't chemical or biological at all. Something that simply arrives, continuously, from every direction, whether the ship's designers plan for it or not. Earth, it turns out, is not just a planet we happen to live on. It is a radiation bunker. One so effective that almost nobody who benefits from it ever thinks about it at all. Above our heads sits roughly 10,000 kilograms of atmosphere per square meter, an invisible column of gas with a shielding effect equivalent to a 10-meter thick wall of solid water, wrapped around the entire planet, generated by a churning core of molten iron thousands of kilometers below our feet, is a magnetic field extending tens of thousands of kilometers into space, deflecting incoming charged particles the way a force field might in a piece of fiction. Except this one is real, and it's been running continuously for billions of years. Together, these 2 systems, the atmosphere and the magnetosphere, reduce the cosmic radiation dose reaching Earth's surface to a mere 0.33 millisieverts per year. Less radiation than you'd receive from a single chest CT scan. A generation ship leaves both of these shields behind, permanently, within the first small fraction of its journey. Beyond Earth's magnetosphere lies a continuous bath of galactic cosmic rays. High-energy protons and atomic nuclei, accelerated to nearly the speed of light by ancient supernovae and other astrophysical violence scattered across the galaxy. These particles are qualitatively different from anything most people picture when they think of radiation. They carry so much raw energy that they pass through solid matter the way a bullet passes through tissue paper. And the shower of secondary particles they generate when they finally do strike a shield can sometimes be more biologically dangerous than the original particle itself. Let's walk through the actual dose math, because the numbers here are precise, and precisely alarming. NASA limits an astronaut's entire career radiation exposure to 600 millisieverts, a threshold specifically chosen to keep excess lifetime cancer risk below approximately 3%. Astronauts aboard the International Space Station, where Earth's magnetosphere still provides substantial protection even in low orbit, accumulate roughly 72 millisieverts over a typical 6-month mission. But out in true deep space, without that protective bubble, the dose rate climbs dramatically. A 2021 study found that even with optimal shielding, roughly 30 grams per square centimeter of protective mass, about as good as physics currently allows, an astronaut could not safely remain in deep space for more than approximately 4 years before accumulating a full sievert of exposure. Nearly double NASA's entire career limit in 4 years. With the best shielding we know how to design. A generation ship voyage of 250 years implies a cumulative radiation exposure potential measured in dozens of sieverts, an order of magnitude, and then some beyond any dose a human being has ever knowingly sustained. What prolonged, low-dose rate radiation exposure across multiple consecutive generations would actually do to human health, including heritable genetic damage passed down to children who never chose to be exposed at all, is not fully understood, and for obvious ethical reasons, cannot be directly studied in advance. The Centauri Dreams analysis states the concern in blunt terms worth sitting with. 250 years of exposure to residual cosmic radiation and its secondary particle showers will damage the DNA of every form of life aboard the starship, not just the human crew, the crops, the livestock, the soil bacteria that make agriculture possible in the first place, the pollinating insects the entire food web depends on, the same insects, remember, that died almost immediately inside Biosphere 2 under conditions vastly gentler than deep space. This is where the radiation problem and the ecosystem problem quietly merge into a single, compounding crisis. Radiation shielding in space ultimately comes down to a question of raw mass, the same atoms that make up Earth's atmosphere. Oxygen, nitrogen, hydrogen can protect against cosmic rays if you simply have enough of them stacked between you and the sky. The question is, how much enough actually turns out to be? A detailed 2019 engineering review estimated that conservatively protecting a human crew on just a 500-day Mars mission, 500 days, not 250 years, would require approximately 1,280 metric tons of shielding mass. For a generation ship habitat large enough to house a genuinely viable population, with interior volume measured potentially in cubic kilometers rather than cubic meters, that shielding requirement would need to scale up proportionally into the millions of metric tons. For comparison, the entire International Space Station, assembled over 15 years across dozens of individual launches, has a total mass of approximately 420 metric tons. The shielding alone for a generation ship could plausibly weigh thousands of times more than the whole of the ISS combined. Some researchers have proposed active shielding instead of raw mass, generating an artificial magnetic field around the ship itself, mimicking Earth's own magnetosphere to physically deflect incoming charged particles before they ever reach the hull. The physics behind the idea is sound, in principle, but it would demand enormous sustained power output and superconducting materials that may not be practical at anything close to the scale required. Nothing resembling this has ever been demonstrated in space. As of right now, it remains firmly in the conceptual phase. A promising idea sketched on a whiteboard, not a system anyone has ever actually built and flown. This is shocking discovery number 3, layered directly on top of the ones before it. The radiation environment beyond Earth's shields is not a background nuisance to be managed with a thicker wall. It is a continuous, compounding threat that grows worse with every additional year of the voyage, threatens every living thing aboard the ship simultaneously, and would require shielding mass on a scale that dwarfs anything humanity has ever launched into space, by not just an order of magnitude, but several. And we haven't even gotten to the question of how you'd actually move a ship carrying that much mass in the first place. Here is where the story moves from extremely difficult into territory that starts to feel less like engineering and more like a wall built directly into the mathematics of the universe. The governing equation of rocketry is called the Tsiolkovsky rocket equation, and it is, without much exaggeration, the single most merciless formula in all of aerospace engineering. In essence, it says this: to go faster, you need more fuel. But that fuel itself has mass, which means you need even more fuel just to accelerate the fuel you're already carrying, and more fuel still to accelerate that additional fuel in an exponential cascade that very quickly stops being manageable and starts being absurd. Think of it this way. If you want to carry a suitcase on a bicycle, you need, at most, a slightly sturdier bicycle. But if you want to carry that same suitcase on a rocket, you need the suitcase, plus the fuel required to lift the suitcase, plus the additional fuel required to lift that first batch of fuel, plus yet more fuel to lift that second batch. Each layer multiplies the one before it. The rocket equation is simply the mathematical expression of this nesting doll of fuel. And the doll grows exponentially, not linearly, with every increase in desired speed. Let's actually run the numbers for a generation ship attempting to reach 10% of light speed, 30,000 kilometers per second, the velocity that would make a Proxima Centauri crossing feasible within a manageable multi-generational timeframe, using the best chemical rocket propellant available, with an exhaust velocity of roughly 4.5 kilometers per second. The required mass ratio between fuel and payload works out to E raised to the power of 6,667. This number is so large that it no longer carries any physical meaning at all. Written out as a power of 10, it would require approximately 2,895 digits. There are not enough atoms in the entire observable universe to supply that much fuel. Switch to ion thrusters instead. Considerably more efficient, with an exhaust velocity around 30 kilometers per second. And the mass ratio drops to E raised to the power of 1,000. Still roughly 10 to the power of 434. A number with 434 digits. Still, in every meaningful sense, utterly impossible. Only theoretical fusion propulsion, an exhaust velocity around 100,000 kilometers per second, a technology that does not currently exist anywhere on Earth, brings the number down into something resembling reason, a mass ratio of approximately 1.35. For every kilogram of payload, you'd need only about 1.35 kilograms of fuel. Genuinely reasonable, as rocket equations go. But controlled fusion propulsion at that exhaust velocity isn't 20 years away, on some optimistic engineering roadmap. It doesn't exist as a functioning technology at any scale, for any duration, anywhere. No fusion reactor built by human beings has yet produced sustained net positive energy output, even in a laboratory, let alone inside a propulsion system rated to run continuously for centuries. Even scaling the ambition down to Project Hyperion's own working target, a more modest cruising velocity of roughly 1.5% of light speed, chosen specifically to make a 250-year voyage plausible, the mass ratios remain punishing. Chemical rockets, still roughly E to the 1,000, still around 10 to the 434. Ion thrusters, E to the 150, roughly 10 to the 65. Still a number no supply chain in human history could remotely fill. Only fusion, again, brings the ratio down to something workable, roughly 1.046. Barely more fuel than payload. And, again, entirely dependent on a propulsion technology that simply does not exist yet. And here's the detail that makes the whole problem even crueler than it first appears. The rocket equation has to be paid twice on any real interstellar voyage. Once to accelerate up to cruising speed, and once again, in full, to decelerate at the destination. Because a ship that cannot slow down doesn't arrive anywhere. It simply shoots past its target star at full cruising velocity and continues on, forever, into the dark beyond it. Since the mass ratio scales exponentially, doubling the total velocity change required doesn't double the fuel needed. It squares it. For a chemical rocket attempting both acceleration and deceleration at 10% of light speed, the resulting mass ratio comes out to roughly E to the power of 13,334, a number so large that expressing it as a power of 10 would require more than 5,700 digits. There is exactly one serious, currently funded engineering proposal for reaching another star system at any meaningful fraction of light speed, and it throws the entire scale of this problem into painfully sharp relief. Breakthrough Starshot aims to propel gram-scale probes, roughly the mass of a single coin, up to 20% of light speed, using a ground-based array of phased lasers delivering a combined 100 gigawatts of power for approximately 30 minutes of acceleration. These probes carry no life support, no crew, no fuel of their own at all. They are, essentially, nanocircuitry riding a light sail. The contrast with a generation ship could not be more total. Breakthrough Starshot is trying to send the rough equivalent of a postage stamp to another star. A generation ship needs to send an entire small city. farms, lakes, forests, factories, hospitals, schools, and thousands of living, breathing human beings. The propulsion requirements between these two projects don't differ by a factor of 10 or 100. They differ by many, many orders of magnitude. No current or near-term propulsion technology bridges that specific gap. And even setting the fuel mass problem entirely aside and asking only about the energy required, the numbers stay brutal. Assume a generation ship with a total mass around 10 million metric tons. A rough, honestly uncertain estimate for a habitat capable of housing tens of thousands of people alongside full life support and adequate shielding. Accelerating that mass to just 1.5% of light speed requires a kinetic energy investment on the order of 10 to the 23rd power joules. That figure is roughly equivalent to a full century of total global human energy production at current rates. Simply getting a generation ship up to cruising speed. Not maintaining it, not decelerating at the far end, just the initial acceleration, would demand an energy investment comparable to everything our entire civilization currently produces across an entire 100 years. This is shocking discovery number 4. The fuel and energy requirements for a real generation ship aren't merely difficult with today's technology. At every velocity that would make the journey survivable within any reasonable number of generations, the numbers stop functioning as engineering constraints and start functioning as something closer to mathematical proof of impossibility. Proof that holds firmly right up until a propulsion technology that doesn't yet exist somehow arrives to change the equation entirely. Suppose, for a moment, that some future breakthrough in fusion propulsion genuinely solves the fuel problem. Suppose the ecosystem problem gets solved too, through decades of future research into closed-loop biology. There remains a third category of failure, quieter than the others, and in its own way just as absolute. The machines themselves would not survive the trip. We actually have direct, real-world evidence for exactly how this plays out, because humanity has already built and flown the most durable machines it has ever created, and we can watch, in real time, exactly how they age. Voyager 1 and Voyager 2, launched in 1977, remain the longest continuously operating spacecraft in human history, nearly 49 years old as of this telling. They were engineered with then state-of-the-art solid-state electronics, radiation-hardened components, and deliberate system redundancy, and they have operated for nearly half a century in one of the most demanding environments imaginable, the deep cold and radiation of the outer solar system, and now true interstellar space itself. And they are dying, steadily, predictably, irreversibly. Their power source, 3 plutonium-238 radioisotope generators, producing roughly 158 watts of electricity each at launch, has been decaying continuously, governed by plutonium-238's fixed 87.7-year half-life. As that output has declined year after year, NASA's mission engineers have been systematically shutting down individual instruments to conserve whatever power remains for the spacecraft's most essential systems. As of April 2026, Voyager 1 has only 2 of its original 11 science instruments still operating. The other 9 have gone dark, one at a time, across the decades, in a slow, deliberate, managed decline. Now hold that fact up against what a generation ship would actually require. Voyager's power decline is happening over roughly 50 years. A generation ship needs to function not for 50 years, but for a minimum of 250 years, 5 times longer, under mechanical loads that dwarf anything Voyager ever experienced. A rotating habitat generating artificial gravity through centrifugal force, full internal atmospheric pressure held continuously against the vacuum of space, water circulating through pumps and pipes, agricultural machinery running around the clock, and the constant physical wear of thousands of human beings simply living their daily lives. As one detailed analysis bluntly summarizes it, our best solid-state space probes, now well over 4 decades old and drifting through interstellar space, would not run reliably for 250 years even if their failing power sources were somehow replaced. And mechanical systems. Anything with moving parts, bearings, seals, rotating joints, fail considerably faster than solid-state electronics do. Consider the specific failure modes a generation ship would need to survive, simultaneously, for 2.5 centuries. Power systems, whatever generates the ship's electricity. Fission, hypothetical fusion, solar power that becomes essentially useless once you're beyond Jupiter's orbit, has to produce consistent output the entire time. Fission reactors degrade as their fuel is consumed, and their structural components become embrittled by decades of neutron bombardment. Structural integrity. A rotating habitat experiences enormous, continuous mechanical stress, and its bearings, seals, and rotating joints wear down year after year, while the hull itself has to contain a full atmosphere of internal pressure against the vacuum outside, without fail, every single hour, for 250 years straight. Life support machinery. Every fan, every pump, every waste processing reactor, every grow light has moving parts and finite mechanical lifetimes. On Earth, we simply replace these components when they wear out. On a generation ship, every single replacement part has to either be carried from departure, requiring enormous storage capacity, or manufactured aboard, which requires raw materials, energy, and precision manufacturing capability, sustained indefinitely. And electronics themselves degrade over time through processes like electromigration and cumulative radiation damage, meaning even radiation-hardened components have finite working lifetimes measured in decades, not centuries. This creates what researchers call the spare parts paradox, and it's worth walking through slowly because it reveals something genuinely elegant and genuinely damning at the same time. To maintain a ship for 250 years, you need spare parts. But you cannot possibly predict every failure mode in advance. And carrying a complete inventory of every conceivable replacement component for every system aboard would add an enormous, likely unsustainable amount of mass. The alternative is to carry the raw materials and manufacturing tools needed to fabricate replacement parts as they're needed. But that requires a genuinely capable industrial base aboard the ship itself. Metal smelting, precision machining, semiconductor fabrication, chemical processing. Each one requiring its own machinery, which requires its own spare parts, which requires its own energy budget, which requires its own trained human operators. The problem becomes recursive. The machines that make replacement parts need replacement parts of their own. The machines that make those machines need parts too. At some point, the industrial infrastructure required simply to keep the ship running becomes as genuinely complex as the ship itself. And the vessel stops being a vehicle in any conventional sense and becomes, functionally, a self-replicating industrial civilization compressed into a single hull. And that industrial base needs a workforce. A single microchip fabrication facility here on Earth typically employs hundreds of highly trained engineers and technicians, supported by sprawling global supply chains for raw materials, specialty gases, and precision equipment that took our entire civilization generations to build up. Aboard a generation ship, that same capability has to be compressed into a fully self-contained system, operated by whatever fraction of the crew can realistically be spared from agriculture, medicine, child-rearing, education, and governance. No rigorous study has ever been published on the minimum industrial workforce actually required to keep a generation ship's systems running for 250 straight years. The problem may simply be too complex for a clean analytical answer, an emergent property of thousands of interdependent systems, each with its own unpredictable failure patterns and maintenance demands, all of them tangled together. This is shocking discovery number 5, the most durable machines our species has ever built. Machines designed with total precision, operating in a genuinely gentle environment with no atmosphere, no humidity, and no human wear and tear, are already failing after less than 50 years. A generation ship needs its far more complex, far more mechanically stressed systems to run 5 times longer than that, with no ground control anywhere in the galaxy to call for help. Set aside the ship itself for a moment. Set aside the engines, the shielding, the recycling systems. There's a problem hiding inside the crew that has nothing to do with engineering at all. A problem written directly into human biology, and it turns out to have a very specific, very inconvenient number attached to it. Every human being carries, quietly, a hidden genetic cargo, a collection of rare, usually harmless recessive gene variants kept silent because they're each paired with a healthy, dominant copy inherited from the other parent. In a large, genetically diverse population, this hidden cargo almost never causes any visible harm. But when a small group of people becomes isolated and begins intermarrying across generations, those rare variants slowly begin finding each other, and the diseases they carry begin, one by one, to surface. This is called the founder effect, and it's been documented repeatedly in real, observable human populations. The Amish communities of Lancaster County, Pennsylvania, descend from roughly 200 founders who arrived in the 18th century, and today carry measurably elevated rates of rare genetic disorders like Ellis Van Creveld syndrome. Ashkenazi Jewish populations, having passed through severe historical population bottlenecks, carry higher frequencies of conditions like Tay-Sachs disease and cystic fibrosis. Finnish populations, isolated for centuries by geography and language, have their own distinct catalogue of inherited conditions collectively known as the Finnish disease heritage. A generation ship, by its very nature, would be the most extreme version of this pattern ever attempted. A small population, completely and permanently isolated, intermarrying continuously for centuries with no possibility of new genetic material ever arriving from outside. In the 1980s, anthropologist John Moore of the University of Florida calculated that a generation ship could maintain adequate genetic health with as few as 150 people, roughly the size of a small hunter-gatherer band, which he argued represented humanity's natural social unit across evolutionary history. This figure entered the scientific literature and was cited widely for decades. Then, in 2014, researcher Cameron Smith of Portland State University thoroughly overturned that estimate using detailed computational modeling. Working alongside William Gardner O'Kearney, Smith simulated population genetics across 30 full generations, roughly 750 years, under a range of different starting conditions using genuine population genetics software. The results were stark, and they escalate in a way worth walking through slowly. A starting population of 150 loses 80% of its original genetic diversity within 30 generations, leaving a population genetically impoverished, dangerously vulnerable to disease, and almost certainly carrying elevated rates of inherited disorders. A starting population of 500 fares only somewhat better, and still doesn't represent anywhere near a wide enough sample of natural human genetic variation. It takes a starting population of approximately 10,000 to reach what Smith identifies as the minimum viable threshold. Enough diversity, in his own words, to set off with a good amount of human genetic diversity, survive even a bad disease sweep, and arrive in numbers and diversity sufficient to make a good go at humanity 2.0. And it takes a starting population of 40,000 to maintain essentially 100% of the original genetic diversity across all 30 simulated generations. The figure Smith identifies as genuinely safe. Here is where the story turns into a genuine, unresolved paradox. Project Hyperion, the most serious contemporary academic effort actually designing a generation ship, constrains its working population estimate to approximately 1,000 people, plus or minus 500. A figure that Smith's own genetic modelling suggests is catastrophically inadequate for long-term population health, and the constraint isn't driven by genetics at all. It's driven entirely by engineering. A larger population requires a larger habitat, which requires more shielding mass, more structural material, more energy, more propellant. Every single problem we've already walked through tonight scaled up in direct proportion to the number of people aboard. This is the central, unresolved contradiction sitting at the very heart of the entire generation ship concept. The population size that human genetics demands is dramatically larger than the population size that current propulsion and shielding engineering can realistically permit. The ship cannot simultaneously be small enough to actually move at a useful speed and large enough to sustain a genetically healthy population across the required number of generations. Not with any propulsion or shielding technology we currently possess, or can even credibly foresee on any near-term timeline. Beyond the founder effect itself, a multi-generational voyage introduces still more biological hazards, compounding on top of one another. Genetic drift. Random fluctuations in gene frequencies that, in a sufficiently small population, can permanently eliminate gene variants from the population entirely, including beneficial ones nobody ever gets the chance to use. Inbreeding depression. A measurable, accumulating decline in overall fitness, fertility, and disease resistance as genetic relatedness within the population inevitably increases across generations of limited choice. And, layered directly on top of everything we covered earlier about radiation, an elevated background mutation rate from centuries of continuous cosmic ray exposure, interacting with small population size and genetic drift in ways that are, honestly, extremely difficult to model with any real precision. There's even a documented risk from pathogen evolution. Research aboard the International Space Station has already shown that ordinary bacteria can mutate into more virulent forms within the space environment. A population living in close, permanent quarters for centuries, with pathogens given essentially unlimited time and opportunity to evolve and adapt, would be genuinely vulnerable to devastating outbreaks in a way no isolated human community in history has ever quite faced. Some proposed mitigations exist, at least on paper. Carrying frozen embryos, eggs, and sperm from a large, genetically diverse donor pool, effectively importing genetic diversity without needing to import the living people themselves. Though this would require reliable cryopreservation technology operating flawlessly for centuries, which does not currently exist. Deliberate genetic screening and directed breeding to minimize inbreeding, which immediately raises deep, unresolved ethical questions about reproductive autonomy that no generation ship proposal has ever fully answered. Gene editing technologies to correct harmful mutations as they arise. Technology that remains, even here on Earth in 2026, genuinely in its infancy, with human germline editing remaining both ethically contentious and technically unreliable. Every one of these proposed solutions is, at present, either genuinely unproven at the century scale required, ethically fraught in ways nobody has resolved, or both simultaneously. This is shocking discovery number 6. Even if every mechanical, ecological, and radiation problem was somehow solved, the crew itself, the actual human population meant to complete this voyage, faces a genetic requirement that current engineering simply cannot house. We need 40,000 people for genetic safety. We can currently, plausibly, engineer a ship for around 1,000. There is one more category of failure left, and it might be the deepest one of all, because it has nothing to do with physics, chemistry, or genetics. It has to do with what happens inside the minds of the people aboard, across a span of time longer than any human society has ever managed to hold itself together. We have real, documented human data on what extended isolation actually does to a well-trained, carefully selected group of people, and it comes from one of the harshest inhabited environments on our own planet, Antarctica. The Antarctic winter lasts roughly 7 to 8 months. During that stretch, research stations are completely and totally cut off. No flights in or out, no ships, no mail, nothing. While mean temperatures hover around -51 degrees Celsius, with recorded lows reaching -85. And in that time, otherwise healthy, highly screened, professionally trained scientists reliably develop a documented clinical condition researchers call winter over syndrome. Depression, insomnia, irritability, measurably diminished cognitive performance, and, in some cases, a genuinely eerie, mild hypnotic state nicknamed the Antarctic stare, or long eye, where a person's eyes simply go unfocused, their mind drifting somewhere else entirely, for minutes at a stretch in the middle of otherwise ordinary conversation. A 2018 study by researcher Gro M. Sandel and colleagues, published in Frontiers in Psychology, documented something more specific still, a phenomenon they termed psychological hibernation. Antarctic Winter Rover crew members, the research found, progressively withdraw from social interaction and reduce their own emotional engagement as the isolation wears on. Not quite depression in the clinical sense, but something closer to the psyche entering a deliberate low-power mode, conserving emotional energy by disengaging from the very social bonds that would otherwise hold the group together. Separate research at McMurdo and South Pole stations found that Winter Rover personnel spent roughly 60% of their available leisure time entirely alone in their own dorm rooms, with a documented lack of privacy and near-constant low-level gossip measurably damaging the group's social relationships over time. Now multiply the Antarctic winter by 375. A 250-year generation ship voyage is roughly 375 consecutive Antarctic winters stacked end to end, with no spring thaw ever arriving to break the pattern. Antarctic stations are, in many genuine ways, the closest real-world analogue we have to a generation ship. Small, isolated groups in confined quarters, no possibility of rescue during the deep winter months, entirely dependent on stored supplies and on each other. But the comparison also reveals, with real clarity, exactly how much easier the Antarctic situation actually is. The winter ends. The sun eventually returns. The planes eventually come back. Every single person at that station knows, with certainty, every single day, that their isolation has a fixed termination date they can count down toward. A generation ship crew has no such comfort available to them at all. For every generation except the very last one, there is no countdown. Only the certain knowledge that they were born aboard a ship they cannot leave, that they will die aboard that same ship, and that their own children and grandchildren will do exactly the same in service of a destination they will personally never see, for a mission they did not personally choose. On a generation ship, this kind of psychological withdrawal wouldn't just be an unfortunate side effect. It could be genuinely catastrophic. The ship's survival depends on constant, active collaboration, monitoring failing life support systems, tending the ecosystem, raising and educating children, resolving interpersonal conflict before it escalates into something worse. People who have psychologically disengaged do not notice failing systems in time. People who have withdrawn do not step in to resolve conflicts while they're still small. People who have stopped caring do not pass the mission's meaning on to their own children. Nuclear submarine crews offer a related, if gentler, analogue. Highly trained personnel, sealed inside a confined metal hull for months at a stretch, operating complex life-critical systems under sustained stress. Research reviewed in a 2026 study notes that isolation from the outside world and from one's own family and friends reliably produces motivational and emotional difficulties among submarine crews. But submarine deployments typically last 3 to 6 months. A generation ship voyage would be somewhere between 500 and 5,000 times longer. And submarines, crucially, can surface. A crew can open a hatch, breathe genuinely fresh air, see open sky, and speak directly to loved ones back home. A generation ship crew can never do any of that. Not once, for the entire length of the voyage. Then there's the governance problem, and it's worth stating as bluntly as the research itself does. There is no period in recorded human history that we know of that lasted 250 years without a major war. The American Civil War took place well over 160 years ago, and it remains, by most measures, comparatively recent history. The extended peace across Western Europe since the end of the Second World War, now approaching 80 years, is arguably the longest sustained period of peace that continent has ever known, and even that falls dramatically short of the 250-year mark. A generation ship is, in political terms, a city-state with no external enemies, no external allies, no possibility of emigration for anyone unhappy with how things are being run, and no possibility of outside intervention if governance collapses entirely. Every single form of government human beings have ever devised — monarchy, democracy, theocracy, oligarchy, military rule — has eventually failed, been overthrown, or been forced to radically transform, usually within a few centuries at the outside. A generation ship effectively demands a political system capable of remaining stable, legitimate, and functionally effective for longer than any political system in the entire recorded history of our species, under conditions of total isolation, with genuinely absolute stakes attached to every failure. And underneath even the governance question sits something even harder to engineer around: the question of purpose itself. The founding generation chooses this mission. They are, by definition, volunteers. Visionaries, or at minimum people who have knowingly and willingly consented to sacrifice the entirety of their remaining lives for a goal they personally believe in. Their children do not choose it. Their grandchildren do not choose it. By the 5th or 10th generation, the original mission may feel less like a living purpose and more like an ancient myth. A story old relatives tell about a green planet nobody currently alive has ever seen, in pursuit of a star nobody currently alive will ever actually reach. This is not speculative fiction. It is simply observed human behavior, repeated throughout our own history. Inherited obligations, dynastic duties, religious missions, family enterprises, reliably weaken with each successive generation that inherits them second-hand. The grandchildren of revolutionaries become bureaucrats. The grandchildren of pioneers become suburbanites. The force of an original conviction seems to decay, roughly, with the square of its distance from the founding event that created it, fading the way starlight fades with distance from its source. On a generation ship, this decay of purpose isn't a philosophical curiosity to be debated over dinner. It's existential. If a middle generation collectively decides the mission no longer means anything, or simply stops maintaining a critical life support system out of apathy, or loses the specific cultural and technical knowledge required to keep the vessel running at all, the entire multi-century enterprise ends. The ship is a chain, and it cannot afford to break at any single link across any single generation for the entire length of the voyage. Philosopher Neil Levy has raised a final, genuinely uncomfortable ethical dimension to all of this. It may be fundamentally unethical to create human beings and then permanently constrain them within a project they never personally chose and can never physically leave. Every single person born aboard a generation ship after its founding generation is, in a very real sense, a prisoner. Not of malice, not of any individual's cruelty, but simply of geometry. They cannot leave. They cannot choose a meaningfully different life. Their career options, their marriage prospects, their entire daily environment, even the manner and timing of their own mortality, were all effectively determined by decisions made by other people before they themselves were ever born. And if a meaningful fraction of the ship's population, at any point across 250 years, does not genuinely consent to the mission, which, by the 2nd generation onward, describes literally everyone aboard, then whether they choose to continue that mission stops being a question of engineering entirely and becomes, simply, a question of human nature. People who never chose a goal cannot reliably be counted on to sacrifice everything for it, generation after generation, forever. This is shocking discovery number 7, and in many ways the heaviest one of the night. Even a perfectly engineered ship, with a flawless closed ecosystem, adequate radiation shielding, functioning machinery, and a genetically healthy population, would still be asking human beings to accomplish something no human society, anywhere, at any point across our entire recorded history, has ever actually managed to do. Step back now and look at everything we've actually tried in the real world across every category of this problem, because the pattern that emerges is remarkably, almost eerily consistent. Biosphere 2's first mission. 8 crew members, 2 years, oxygen collapsing from 20.9% down to 14.5% through an unanticipated chemical reaction with the building's own concrete. External oxygen injections required twice. Most vertebrate species and nearly all pollinating insects dead. Roughly 10% of the total atmosphere leaking away every single year. Biosphere 2's second mission. 7 crew members, intended for 10 months, collapsed after 6 due entirely to human interpersonal conflict and management disputes, with 2 crew members forcibly removed mid-experiment. NASA's own International Space Station water recovery system, a genuine, celebrated 98% closure rate, and still, unavoidably, a 2% loss that would compound into complete failure over any timescale longer than a few decades. The Mars 500 experiment. 6 crew members, isolated together for 520 days in a sealed Moscow facility, experiencing measurable circadian rhythm disruption, steadily decreasing physical activity, and documented depressive symptoms, despite every crew member knowing the experiment had a fixed, guaranteed end date, and Voyager 1 and Voyager 2, our 2 longest surviving spacecraft, now approaching 49 years old, already reduced to a small fraction of their original operational instruments, requiring continuous active management from ground control just to keep functioning at all. The lesson threaded through every single one of these real-world experiments is consistent, and it's worth stating plainly because it applies with equal force to the ecological, the mechanical, and the psychological dimensions of this problem all at once. We have never built a closed system, ecological, mechanical, or social, that could genuinely sustain itself for more than a handful of years. Every successful long-duration system humanity has ever actually operated, the ISS, Antarctic research stations, nuclear submarines, depends, without exception, on 3 specific safety nets: external resupply, external rescue capability, and a clearly defined endpoint that everyone involved knows is coming. A generation ship, by its very design, removes all 3 of those safety nets simultaneously, permanently, for the entire duration of the voyage. It would be easy, after everything we've just walked through, to conclude that generation ships are simply permanently impossible, that humanity is forever trapped within our own solar system, and that the stars are, and will always remain, entirely beyond our reach. That would be the wrong conclusion to draw, and it's worth being genuinely precise about why. The real problem isn't that the universe forbids interstellar travel. The real problem is that we're currently trying to solve what is, honestly, a problem for a far more advanced civilization using the tools of our own. Every single failure mode we've covered tonight isn't a law of physics standing permanently in the way. It's a gap. In our engineering, our biology, our materials science, our social science. And gaps, unlike laws of physics, can genuinely be closed. Let's walk through, briefly, what would actually have to change, category by category, for a generation ship to become genuinely plausible. Not necessarily for reaching Proxima Centauri specifically, but even simply for reliably crossing the outer edge of our own solar system. On propulsion. No chemical, nuclear thermal, or ion system can move a generation ship at any genuinely useful speed without fuel demands that mathematically dwarf the ship itself. The most promising path forward remains fusion propulsion, which could provide exhaust velocities high enough to bring the mass ratio down into something manageable. But controlled fusion has famously been 30 years away for roughly 70 years running, and no fusion reactor built anywhere on Earth has yet achieved sustained net positive energy output in any practical, useful sense. If it ever does become practical, it would genuinely transform this entire equation, turning physically impossible into merely extraordinarily expensive. Other proposed paths include scaled-up beamed energy propulsion, building on the breakthrough Starshot concept but at a scale nobody has seriously attempted, and the possibility of refueling directly from Oort cloud material during the multi-century crossing itself. Mining hydrogen from icy bodies along the way, using autonomous infrastructure that would need to be established centuries before any ship ever departs. On closed life support, the fundamental problem is that we do not yet fully understand how Earth's own biosphere actually works. Earth is, in a meaningful sense, a closed system that has sustained life continuously for roughly 3.8 billion years. But it was never designed. It evolved, slowly, through billions of years of co-evolving relationships between millions of interacting species, each one adjusting endlessly to all the others. We cannot simply replicate that stability by assembling a curated list of species inside a sealed box and expecting it to hold. What would genuinely need to change? A far deeper understanding of microbial ecology at a systems level, comprehensive atmospheric chemistry modeling that accounts for how every single structural material interacts with a sealed atmosphere over centuries, and closure rates approaching 99.99% for every material cycle. Nitrogen, carbon, phosphorus, potassium, sulfur, and every trace element life actually depends on. Not an incremental improvement over what we've already achieved. A genuine qualitative leap. On radiation, this may be the single hardest category to solve because it is pure, unforgiving physics. You cannot negotiate with an incoming cosmic ray. In situ shielding, gathering raw mass from asteroids or Oort cloud material during the voyage itself rather than launching it all from Earth, could help enormously, since gathered mass never needs to be accelerated to cruising speed in the first place. Active electromagnetic shielding, generating a field powerful enough to mimic Earth's own magnetosphere, remains genuinely aspirational. The power requirements would be enormous, though a working fusion reactor might conceivably supply them. Pharmaceutical radioprotection, enhancing the body's own DNA repair mechanisms, remains an active area of ongoing research, though nothing proven effective yet against the specific high-energy particles that dominate deep space. And there's even a genuinely strange biological angle. Certain organisms on Earth, like the bacterium Deinococcus radiodurans, already possess extraordinary natural radiation resistance. Understanding, and perhaps someday adapting, whatever mechanism grants that resistance remains far beyond current biotechnology. But it isn't physically impossible. On mechanical reliability, a 250-year mission demands a genuine paradigm shift, from systems that are periodically maintained to systems that actively maintain themselves. Self-repairing materials, inspired by biological healing processes, could detect and repair their own cracks and corrosion. Early research already exists in self-healing polymers, though nothing close to century-scale reliability yet. Modular, hot-swappable architecture, with automated diagnostics routing around failures the way internet traffic routes around a downed connection. Genuine onboard manufacturing capability extending eventually towards something resembling molecular-scale assembly, and deliberate redundancy at the whole system level. Not one life support system, but 3 or 4 fully independent ones, any single one of which could sustain the ship alone if the others failed. And on population and society, arguably the hardest category of all, because it cannot be solved through engineering alone. If Cameron Smith's estimate of 40,000 people is correct, and it currently remains the best available figure, the ship simply has to be large enough to house that many people, which in turn demands breakthroughs in propulsion to move that mass, shielding to protect that volume, and life support to feed that population, all of which are already tangled together into a single coupled problem. Smith himself recommends sending a fleet of multiple ships rather than a single vessel, so a disaster aboard one doesn't end the entire venture, and so the ships can trade resources and maintain a larger effective social and genetic network across the whole fleet, carrying cryopreserved genetic diversity, frozen gametes and embryos from thousands of donors, could supplement a smaller living population without requiring those additional people to physically be aboard, assuming reliable century-scale cryopreservation technology, which does not currently exist, and deliberate cultural engineering, developing education systems and shared narratives capable of transmitting genuine purpose across generations, not through coercion, but through something closer to how a religion or a civilizational project sustains itself, something people genuinely choose to believe in and voluntarily pass on because it gives their lives real meaning, rather than something imposed on them by ancestors they never met. Governance itself would need to be deliberately designed for multi-century stability in a way no political system in history has ever attempted. Perhaps something closer to a constitution with built-in mechanisms for its own evolution, or an AI-assisted governance system capable of detecting social breakdown and mediating disputes before they escalate into something the ship cannot recover from. Here, finally, is the honest tally. With current technology, a generation ship cannot work. Not because the universe forbids it, but because we have not yet learned how to build a closed ecosystem that sustains itself for centuries. We've tried and failed at just 2 years. We have not learned how to shield a large enough habitat from cosmic radiation for centuries. The required mass is genuinely staggering. We have not learned how to propel a city-sized mass to any useful cruising speed. The fuel requirements are exponential with every propulsion technology we currently possess. We have not built machines that run for centuries without external maintenance. Our very best have lasted 50 years, and they are already failing. We have not learned how to maintain genetic health in an isolated population at the scale required. We need 40,000 people, and current engineering permits something closer to 1,000. And we have never once, in the entire span of recorded human history, sustained social cohesion and shared purpose for longer than any civilization has ever actually endured. Each one of these, on its own, is a genuinely hard problem. Together, they compound into something worse than the sum of their parts. Larger populations require larger ships, which require more shielding and more propulsion, which require more energy and more fuel, which require larger supporting infrastructure, which requires more maintenance, which requires more people, which requires, again, a larger population. The constraints form a single coupled system, and with the technology we currently possess, there is no feasible intersection point anywhere inside it. But none of this, not one item on that list, is a law of physics. Every single item is a gap in our current capability, and gaps, unlike laws, can be closed by advances in fusion energy, biotechnology, materials, science, ecological science, and social science. Over however many decades or centuries it eventually takes us to close them. The generation ship, in the end, is not really a test of whether interstellar travel is possible in principle. It's a test of whether we can become the kind of civilization capable of actually building one. Before we close, let's sit with the scale of everything we've walked through tonight, all together in one place. A journey of 4.2 light years, requiring, at any speed we've ever actually achieved, tens of thousands of years to complete. A span of time longer than the entire existence of recorded human civilization many times over. A first leg of that journey simply escaping our own sun's outer gravitational shell that alone would take roughly 300 years. Longer than the United States has existed as a nation. A closed ecosystem that has never, in a single real-world attempt, sustained even 8 trained people for more than 2 years, let alone tens of thousands of people for 2.5 centuries. A radiation environment that would exceed a human being's entire career safety limit within roughly 4 years, even with the best shielding physics currently allows us to design. A fuel requirement that, expressed honestly, produces numbers with thousands of meaningless digits. Mathematics quietly refusing to cooperate with the ambition behind it. A population requirement of 40,000 genetically diverse people set against an engineering reality that currently permits something closer to a single large village. And a social and political requirement, multi-century cohesion, sustained purpose, functioning governance, that no human civilization anywhere across our entire recorded history has ever actually managed to achieve even once. Every one of these numbers, taken alone, sounds like a single obstacle. Taken together, they describe something closer to a message, quietly encoded into the physics and biology of the universe itself. Not yet. Not never. Not yet. There's something worth genuinely sitting with here, now that we've walked through every category of failure this idea would face. When we ask, seriously, whether we could actually build a generation ship, we are not really asking a narrow engineering question about mass ratios and shielding thickness. We are asking something considerably larger and more honest. What kind of civilization are we, right now, in this moment? And what kind of civilization could we, eventually, become? The answer, for now, tonight, is simply, not yet. But the question itself remains worth asking, seriously and carefully, precisely, because the specific things we would need to learn in order to eventually answer it differently. How to build a genuinely closed ecosystem that doesn't quietly poison itself with its own concrete. How to shield living things from radiation across centuries rather than years. How to sustain a functioning community's shared purpose across dozens of generations without it decaying into apathy or collapse. Are things worth learning regardless of whether we ever actually build a ship to fly to another star. They are, in fact, things our own species needs to learn for reasons far closer to home. A planet is, after all, also a closed ecosystem. It also has a finite capacity to absorb waste and recycle what it's given. It also depends on the quiet, uncelebrated labor of pollinating insects and nitrogen-fixing bacteria that most of us never think about until they begin, one by one, to disappear. Every one of the 6 deep, compounding problems we walked through tonight, closed-loop ecology, radiation resilience, energy at civilizational scale, machines that endure, genetic and population health, governance that survives longer than any government in history, is a problem our own civilization is already quietly working to solve, here, on the one planet we currently have, whether or not a single generation ship is ever built. The generation ship, in that light, stops being simply a doom story about an impossible voyage and becomes something closer to a mirror, an unusually clarifying, unusually honest thought experiment, forcing us to name, with real precision, exactly what a civilization would need to master before it could sustain itself indefinitely, in complete isolation, with absolutely no possibility of rescue. We are, it turns out, already living inside a version of that same experiment. We simply haven't sealed the doors yet. Picture it, one last time, before we close. Somewhere in an unbuilt future, decades from now, or centuries, a ship departs. Not tomorrow, not soon, but eventually, if enough of tonight's gaps are ever actually closed, aboard it. Thousands of people, none of whom will ever see the star they're traveling toward. Around them, forests grown under artificial light, water endlessly recycled through pipes engineered to leak less than a fraction of 1%, a magnetic field of their own making, humming quietly, deflecting a ceaseless rain of cosmic particles that would otherwise, slowly, damage everything alive aboard. The first generation departs knowing, with total clarity, exactly what they're choosing to give up. The second generation is born already aboard, inheriting a mission they never personally agreed to, in a world with no outside, no elsewhere, no possibility of choosing differently. Somewhere around the 5th or 10th generation, the green planet their ancestors once stood on becomes something closer to a bedtime story. Half remembered, half invented, told to children who have never once felt real wind, real rain, real unfiltered sunlight on unprotected skin. And still, if everything holds. If the concrete never quietly steals the oxygen, if the nitrogen keeps cycling correctly through soil bacteria nobody thinks about, If the shielding holds against radiation for 2.5 centuries straight, if the machines keep repairing themselves faster than they wear out, if the population stays genetically diverse enough to survive whatever disease eventually finds them, if the governance holds together longer than any government in the entire history of our species, and if, generation after generation, enough people keep choosing, freely and without coercion, to care about a destination they will personally never see. Then, eventually, centuries after the first generation ever stepped aboard, one final generation looks out through a window that has never shown them anything but stars and sees, for the first time in the ship's entire existence, a new one growing larger. Not just brighter, larger. Close enough, finally, after hundreds of years, to resolve into an actual, distinct, individual star, rather than one indistinguishable point among the countless others surrounding it. They will have never known Earth. They will have been born, lived, and will someday die, entirely aboard a moving world built by people who died centuries before they themselves were born. And yet they will be the ones who finally arrive. The ship is a chain. It cannot break at any single link across any single generation for the entire length of the journey. Tonight, we've walked through every place that chain would currently, honestly, most likely break. The ecosystem, the radiation, the fuel, the machinery, the genetics, the simple, fragile, essential human willingness to keep caring about something larger than any one lifetime. We don't yet know how to forge a chain that doesn't break. Not for 250 years. Not yet. But we are, even now, tonight, the kind of species that keeps asking exactly how it might be done anyway. Measuring each specific gap with real precision, rather than looking away from it. The same patient, unglamorous work that once let a closed system on Earth teach us, through painful and total failure, exactly what a truly closed system actually requires. Tonight we asked why a generation ship would fail before it ever left our own solar system. And the honest answer turned out to be layered, specific, and far more instructive than a simple, "it's impossible," could ever be. We found that the true edge of our solar system, the Oort cloud, not the heliopause, and certainly not Pluto, lies so far out that simply crossing it would take a minimum of roughly 300 years, meaning any generation ship must first survive centuries of travel before its true interstellar voyage has even properly begun. We found that every closed ecosystem humanity has ever actually built and sealed shut has failed, and that the most ambitious attempt, Biosphere 2, collapsed not primarily from some dramatic engineering failure, but from an ordinary building material quietly stealing oxygen directly out of the air. We found a radiation environment so severe that even the best shielding physics currently allows exceeds a human being's entire career safety limit within roughly 4 years, threatening not just the crew, but every crop, every pollinator, every strand of soil bacteria the ship's entire food web depends on. We found a fuel and energy requirement so extreme that, at every velocity that would make the journey survivable, the mathematics itself produces numbers too large to hold any physical meaning at all. We found that our most durable machines, the Voyager probes, are already failing after less than 50 years, a fraction of the 250-year minimum a generation ship would require. We found a genetic requirement, 40,000 people for lasting population health. That current engineering can barely support at 1/40th that number. And we found that no human society, anywhere, across the entirety of recorded history, has ever sustained itself, stably and cooperatively, for as long as this voyage alone would demand. None of this, taken individually, is a law of physics forbidding the attempt forever. Each one is a gap, in propulsion, in biology, in materials, in our understanding of each other. And gaps, unlike laws, can eventually be closed. The generation ship is not a story about the impossibility of reaching the stars. It's a mirror, held up to whatever civilization eventually attempts it, showing them, with unusual clarity, exactly what they would need to have already learned about themselves and about their own fragile, life-sustaining world before they could ever hope to carry a fragment of it somewhere else. We are not that civilization yet, but we are, tonight, the kind of species that keeps asking the question anyway, measuring the gap with real honesty rather than looking away from it. Sleep well tonight on a planet that has already been running the only truly successful closed-loop life support experiment any of us has ever known. For 3.8 billion unbroken years, without a single generation ever needing to ask whether the chain would hold. Good night, and rest well under the stars, and under the quiet, patient work of everyone, everywhere, still learning exactly what it would take to one day reach them.